I'm going to continue just where I left off from the last screencast. I'm discussing parameterizations of spirals, and we considered the Archimedean spiral, which is given by in this form. I now want to turn to the logarithmic spiral, the other important spiral, and that's given r of t is equal to e to the at cosine t, e to the at sine t. Now t is, in this case, a real number, and I will go ahead and label this because I already said it. This is just a logarithmic spiral. Oh, actually, I put that in a bad place. But in any case, look, this now seems clear from the previous discussion. What I have here now is my r of t, my t-dependent radius. Keep putting this in quotes. Is simply here e to the at. So you can see what that will look like, or you can attempt to plot what it will look like, and then you'll see what it looks like. So let's draw some coordinate system. And these are actually rather difficult to draw for reasons that will now be clear. Let's get some points and do a table. So t equal, now I can do t equals 0. When t is equal to 0, r is equal to 1. When t is equal to 2 pi, go around once, 2 pi, r is equal to e to the 2 pi a. So for one thing, if I have sort of normal distances on these axes, a better be fairly small, or I'm going to have gone, suppose a were 1, I will have gone e to the 2 pi, which is a pretty big number, just going around once. So it's a good idea to make a kind of small number here. I'll just do, well, you can see, you hardly need me to write these things. The radius now will be equal to e to the 4 pi a, and the fact is it's growing exponentially with the number of turns of the spiral. All right, so let's just let's see what we can do here. So here we are at 1. All right, and then we'll call this, well, again, you know, that if that's 1, I'm in trouble. Fill that back in. So let's put 1 here. I'll put e to the 2 pi a there. Well, I guess a isn't very big, so here's e to the 2 pi a. Now e to the 4 pi a, well, that's, in this case, it's just the square of that. I don't know where that is, but I'll just look. I'm going to show you a picture in a moment, a computer generated picture, etc. And then now I can go inwards too. Well, let me just draw the outwards parts first. So let's give it a go. See what we can do here. I'll do it in bold. I'm going to start here. Let me just say what before I draw. I'm going to start here. I'm going to spiral out, and I'm going to hit that point, and I'm going to spiral out, and I'm going to hit that point, etc. So let's just go. So go. Start here. Go around, and I spiral out. That's probably something like what it looks like. Let me just go ahead and draw it spiraling in. Now you'll see here, let's just do a few of these. Oh, let me go ahead and put the arrows indicating orientation. I like to do that. Let's just put one more value here in this table. I'll let you do the rest at home. That's t is equal to minus 2 pi. Right, that corresponds to the first inward spiral here, minus 2 pi. So what is this? R is equal to e to the minus 2 pi a. So that's a number less than 1. And I've spiraled inwards. And I can continue that going backwards in t. If I said time, I mean t. Forwards and backwards. Anyway, so this is what it looks like. And as I said, it's called a logarithmic spiral. And let's have a quick look here and contrast these. So this is my logarithmic spiral, again plotted with MATLAB. Again, a finite piece of it spirals infinitely often going into the origin here, and as well as outwards. And you can see the contrast between the logarithmic spiral, which you might think would be called an exponential spiral, but it's not. Anyway, the logarithmic spiral and the Archimedean spiral. Here we see the equal spacing, and here we see, if you look at a fixed value of theta, let's say along the positive x-axis here, you'll see that the radius is growing exponentially with each turn, whereas here it's equally spaced. All right, so this. Apart from introducing and making sure you're familiar with these two particular kinds of spirals, the important point here really is the more general point, which is that when we'll consider parametrizations that are of the form, again, a cosine and a sine term with the same prefactor, which will be a function of t, and that will give you some sort of motion, circular motion, together with a t-dependent radius. Now, it may not just continually spiral out, it may do something more complicated. I'll get onto that when we do sketching and when you do your homework, but that's the general principle that I want to convey. And I think that'll end the subject on spiraling.